All right. So we're into factorial designs, okay? And we talked about factorial design being designs where I have multiple categorical factors. So I have multiple categorical IVs where I'm interested in looking at the unique and interactive effects, unique and combined effects of these different factors on some type of continuous outcome, okay? Identifying our factorial designs by the number of levels of each analyzed factor. Pretty slick notation so that we're easily able to communicate exactly what's going on. What are my IVs? What are my DVs in the classic sense? And how do they mix together, right? Talked about cells. These are individual subunits, right? In the cross design, our main effect, these are, think about these as column and row effects in a two-factor ANOVA, right? And when we get into three-factor, then we get into three-factor or three-dimensional space and so on, and it gets tricky. Thinking about our main effects as being row and column effects. Collapsing across this factor, what's the difference across individuals exposed to this or this condition? Collapsing across this other one, how do we see differences moving? These are the effects of one factor on the DV at another at different levels of the other one. So here we're going to get into when we get into some of these interaction effects, talking about these conditional effects, where if you ask me what's the effect of X on Y, say, Matt, you say, what's the impact of this manipulation on our outcome? I would say, I don't know. What level of the other manipulation are we looking at, A, B, or C? Because it differs, it kind of changes, right? So here, talking about folks from Alabama and other portions of the difficult South, where we start to get problems with both heat and humidity and recognizing, or people from Chicago, where you've got heat and cold sort of moving together, and also heat and humidity, which is the worst of both worlds, right? Talking about Fairbanks, Alaska, right? Where we start to see the impact differing across differing levels with stuff, right? So we've got factor A here, factor B. What's the impact of both heat and humidity on performance, right? And so we've got a number of different effects we can look at that are going to correspond to different effective factor A on outcome. What's the effect of humidity on performance, right? Collapsing across temperature. If I just look at people performing in a high humidity versus low humidity, what's the difference that I see there, right? So we're looking at totals here. We can also ask, what's the effect of factor B on outcome? What's the impact of temperature on performance? Ignoring humidity levels, if we're scores for people in 70, 80, and 90, what's going on here? This is essentially kind of versions or analogs of our one-way ANOVA designs, okay? But then, kind of where these factorial designs come into play and start to become interesting. What are the combined effects of factors A and B on outcome, okay? What's the impact of specific combinations of temperature and humidity on performance? As I start to put these components together, how does this impact how people are operating? Here, ANOVA, right? So it's a two-factor ANOVA. So I got two IVs, right? We've got two levels, the first three levels to the second. So we have distinct populations. This starts to become important when we start thinking about if we do have an interaction, suggesting that we do need to go and look at these conditional effects. How many distinct populations are we dealing with? How big is the design? How many people do I need to go through and populate this? Amanda, I usually make fun of Narina students. You're as close as we get. Like I've got a 2 by 3 by 3 by 2 by 4 factorial design. Friggin' yikes! Like this. Look at less factors. There's way too many factors. So to cut down on factors, but it's just a function of like jury stuff. Like I want to see like what race, sex, sort of political viewpoints, and personality all impact on this. We're like, well, yikes, that's a lot of stuff, and God help you if you actually get like a four-way interaction trying to tease out what the hell's going on with that. So being mindful of our designs and sort of the stuff that's going on there. Okay, so main effects. You can look at the main effect of humidity. My hypotheses here, comparing low versus high, or so our null effect or null hypotheses here is that performance for null is equal to performance, right? Here, this row effect, our F statistic, we're going to look at over the expected variability of, okay. Hypothesis is true Bosch. First, to be identical to one another, even if really humidity has no impact on performance. No, probably not impact, right? There's probably going to be some little bit of a difference, right? But variability that I'm seeing across these means starts to really exceed what I would expect just due to random sampling error. That's when my F statistic is going to, that F ratio is going to start larger, getting larger. And as that F ratio starts to get larger, Basha, what's more likely to happen in terms of my test? Yeah. Yeah, right. Because my F ratio is going to get bigger. That numerator is going to get bigger than the denominator. As that increasingly gets proportionally bigger, I've got a bigger F ratio, and I'm more likely to also have a main effective temperature here. My null hypothesis here is 70, 80, 90 degree performance. Means are all different, equal, equivalent in larger population. Alternative hypothesis here is that mean performance differs in at least one of these temperature conditions. Okay, Teresa, why did I write that out? Why can't I just use symbols for my alternative hypotheses there for temperature? Yep. This is my omnibus test. In our omnibus test, in our ANOVAs, if I have more than two groups, I can't say where that difference is. Now, for the main effective humidity, that's easy. I just look at which one's higher, and then I say like that one, right? But with this, when we got more than more than two conditions, it's hard to go through and identify exactly where that difference is going, right? So here, again, we're going to talk about observed variability across our temperature means. Down here, these columns at the bottom, over the variability if the null hypotheses were true, okay? And so in ANOVA speak, Katie, ANOVA speak, so when we talk about variability, what does variability mean? What are we referring to there? Okay, and distance is another word for, think about ANOVA stuff. Not necessarily air, no, and particularly here, right? Because this is sort of the systematic effects. Yeah. Variance in ANOVA, what are we talking about if we're talking about variability variance? Anybody remember? Did you startled, right? Yeah. What we're just talking about, sort of conceptually, we're just talking about differences. If I see variability, it just means differences. So distances, yeah, literally distances, but literally differences across these means, right? Because I can't just say, oh, the difference between A and B or the difference between 75 and 80 or whatever, because there's lots of differences. There's lots of ways that this can be different. And so what we do remember in this ANOVA approach is we just switch over and we start talking about variability. Variability is our measure of differences in our data. So observed differences across temperature means over observed expected differences if the null hypotheses were true, okay? So just in terms of thinking about how we use these concepts and think about this flexibly. So again, if we're in ANOVA and we see variability, we're just talking about differences, okay? Anytime we talk about variability, we're talking about differences in scores, right? I've got high standard deviation, that's a measure of variability. It just means that scores are more different in this group than they are in the other group on average, right? So just thinking flexibly about our terms, okay? All right, questions about this? All right, so our interactions, all right? These designs, we can start through and look at some cool influences. One level of our, or one factor on the impact action effect, looking at variability or differences across our individual cells, okay? Which start to exceed what we would expect the types of differences to be, or varying, or sort of not the same type of differences we would expect from what we're seeing in our overall main effects, okay? This is maybe one of the most important bullet points in this whole lecture series, okay? Thinking about how do we think about or interpret interactions, okay? An interaction just conceptually says that the nature of one effect, the nature of an effect of one factor on the outcome depends on the second one. There's a dependency in there when we have an interaction. It says that the impact of heat on or temperature on performance depends on humidity. So if you ask me about the temperature of, or the impact of temperature on performance, I can't tell you, because the impact of temperature on performance depends on whether or not what the level of humidity are. Those two things are intertwined, so that I can't really interpret that main effect. I might have a main effect, but I can't interpret it. Anytime someone says, hey, Elizabeth, there's an interaction of A and B on my outcome, what does that mean? What's up? It tells you everything you need to know about it, because, yeah, right, see, there we go, corrective information, because of this bullet right here. Without knowing anything else, you could say, well, it seems like the impact of factor A is dependent on factor B, right? And you don't know what those factors are, what your outcome is, but it tells you exactly what's going on with that effect, okay? And so if, yeah. No, there's no directionality yet. We need to jump in and we can then start to tease apart and sort of look at stuff. But again, an interaction is just an omnibus effect. Again, it just says the effect of sort of my first one factor is dependent on level of the other factor. I don't know exactly how, but that's just what's going on, right? So in the design where Amanda has like a four-way ANOVA model and finds a four-way interaction, I could say, well, it looks like sort of the effect of these factors are all independent on each other in one way. How we actually tease that apart and figure out what's actually going on in the interpretation, that's a puzzle to solve. I mean, you can do it, but we start to sort of worry about interpretability and things like that. But anytime I see an interaction, this is going to carry on into next. What's another name for an interaction effect? Do you know? Teresa, you have some regression background. If we're talking about interactions, what are we talking about? Moderation effect, okay? Moderation, it says the relation between X and Y is dependent on some other factor, right? How these two things relate really depends on some other factor or factors, depending on the level of interaction that's going on, right? Again, regression, these factorial designs are just a special case of regression. And when we start into getting into situations where we have violations of our underlying like homogeneity of variance and stuff like that, SPSS again has finally worked in some ways to go through and some robust tests to do. But when we do that, we're switching over to a regression format, so the output will look different with that than we would with a normal ANOVA design. But what we can do, if we understand how these things all work together, we can be flexible in terms of how we're thinking about things and how we're approaching our analyses in order to get in applied setting what usually ends up being the least bad of our options, okay? So if we're thinking about, so again, remember this, if I'm talking about an interaction, it just means the effect of one factor on an outcome depends on some other factor, okay? So our current example here, interaction would suggest that the impact of humidity on performance is dependent on temperature, okay? What's the impact of humidity on performance? Does it make it better or worse? But I don't know, it really kind of depends on how hot or cold it is, right? Also important to remember that there's no inherent direction to these interactions. This is a conceptual issue. I could also talk about this is the impact of temperature on performance depends on humidity, right? So this is another point where you really have to have a good sense for conceptually what makes sense. What what factor ends up makes the most sense is kind of the primary driver, and then what's the factor that's the moderating factor, that's the one that's maybe changing the nature of that association. All right, so in addition to my two main effects, I also have an interaction, let's say, of humidity by temperature. Null hypotheses, and again, there's no statistical notation for this. It just says the effect of humidity on performance is independent of temperature, doesn't depend on temperature, is, our alternate hypothesis here is that the effect of humidity is dependent on temperature, or we can flop that around. So again, this really depends on reading the problem, understanding sort of what we're trying to do, what the existing literature says. Generally, the thing that's already been established over and over and over and over and over again is generally the thing that we think about as the main or the base conditional effect, and then sort of the new novel thing is kind of sort of how we might think about that as moderating that. So Sam, if we know what's a relation that's well established in the eating disorder literature? No, just a straight up relationship. Yeah. Restraint and restriction. Restraint. Okay, so cognitive intention to restrict and restricting behavior, there's a strong correlation between that. Okay, so if you said, hey, I've got a paper, then I found a correlation between restricted intention to restrict and restricted behavior, would anybody be interested in that? No one's going to be interested in that, right? But does intention to restrict always hold the same relation with restrictive behavior across everybody universally the same way always for everybody? No, right? So now we're talking about moderators. What are factors that start to change the strength of that relationship, right? And now all of a sudden we've got a more interesting question that probably gets into some of the nuances of this behavior. This is where we're talking about our interactions, okay? What probably wouldn't be good is like talking about, oh, hey, here's the relation between sort of random thing that no one knows about and sort of outcome and restricting behavior, and cognitive intention is the moderator. Like, well, you can do it mathematically, it doesn't make any difference, but that's probably a harder thing to set up conceptually than the other way around. Okay. People kind of get an idea of what we're talking about in terms of these interaction terms. Okay, so here again, we've got our outcome. Are we, Josiah, does it look like we have, do we have a main effect of temperature or humidity here, Josiah? Maybe, I mean, sort of guessing. Yeah. Just main effect, yes or no? Yeah, probably, right? I don't know. Performance in our low humidity condition, collapsing across temperature, higher than performance humidity. So in general, ignoring temperature, it looks like people are tending to perform better in low humidity versus high humidity. Okay. Josiah, what about, do we have a main effect of temperature here? Yeah, maybe it looks like sort of an increasing thing where temperature or performance looks like it's decreasing as we go and increase in temperature and whatever this task is. Do we have an effect here, Josiah? Yeah? Okay, so let's look across, if we just look at low humidity, right? What's happening to humidity what's happening to performance as temperature increases at low humidity? It goes down. We have about 5 units down. If we look at high humidity, what's temperature doing, or what's performance doing as temperature decreases? Going down by about 5. Across high and low, what's the difference in performance across high and low humidity at 70 degrees? 10. What about here? 10. So is there anything going on in these cells that doesn't look like it's sort of different than what we're already seeing in the main effects? No. So we probably would say that doesn't look like there's much of an interaction in these data here, okay? But what if we look at, say this, go back to you, Josiah. Does it look like we have a main effect of humidity? Yep. Is that different than before? Nope. What about a main effect of temperature? Is that different than before? What's going on different in the cell means though? Okay, so at low levels of humidity, it looks like, is there an impact of temperature on performance? Nope. Looks like at low levels of humidity, 70, 80, 90 degrees for this test doesn't matter at all. What about if we bump the humidity up? Then what happens? Then temperature matters a lot. Now we're seeing systematic large decreases in performance if we're operating these at high levels of humidity. This is what an interaction looks like. Again, our main effects don't look any different than the previous, but we're seeing something that looks like an interaction now. So depending on whether I'm talking about low levels of humidity or high levels of humidity, starts to impact what's happening in terms of performance. So this is an important thing, remembering that you'll probably run into this at some point, right? Main effects and interactions independent of one another. You don't need to have main effects to have an interaction. You don't, sort of vice versa. You'll get this sometimes, people who like, oh, you can't interpret an interaction because you don't have any main effects. Like, well, that's patently wrong. It's just like everything about it. There's nothing right about what you've just said here, right? Because these two things are by definition independent of one another. Okay, so looking at just cell means can be difficult. It's hard. We kind of have to go through and analyze. So what you should always do, anytime you get an interaction effect, first thing you do, Emily, you plot it out. Don't try and sit there and sort of talk about what the hell is going on with what. Get an Excel, grab a sheet of paper, plot it out. What is going on? Because as soon as you plot this out, it's very easy to quickly see what's happening. Okay, so this here is the first example. If we see here, we've got parallel lines. The relation of linear increase in temperature on performance is the same across high and low levels of humidity. We bump up performance decreases, but it decreases at the same rate as it does in high levels of humidity. So we're good here. At 90, 80, and 70 degrees, it's the same, right? People tend to perform better in low humidity than high humidity, and tend to perform better at lower temperatures, at least sort of at 70 than 90. But that's the end of the story. There's nothing else much more going on there. This is the second example. These are our second set of data, right? And Kitty, what's going on at low levels of humidity in this graph? It's stable. Temperature doesn't impact it at all, right? I could be whatever the hell temperature I want. It doesn't matter, because at least in between the bounds of 70 and 90, my performance doesn't change at all, right? But what happens if I sort of crank up the humidity in the room? Then what happens is my temperature increases in this graph. Or at high levels of humidity. Sorry about that. It goes down, right? So if I get a much different effect at high levels of humidity than I do at low levels of humidity. And so here, if we don't have any interaction, what we generally see is parallel plots, right? They're sort of basically doing about the same thing. When we get an interaction, we're seeing sort of cross effects somewhere in there. Maybe not within the bounds of, but eventually if we carried it out, they would cross at some point. So again, pulling this out of Howell, we're seeing in this first panel, these are different patterns of means that aren't suggesting any interaction, right? And they're all parallel across each one of these. Interaction effects, we're seeing very different things across these different different levels, okay? Very, very easy to see an interaction, and starts helping you understand exactly what's going on, how we might probe this as soon as we plot this out, okay? So as soon as you get anything that looks like it might be an interaction, stop everything, grab a sandwich, and just get in Excel and just start plotting this out. so you can actually see what's going on. Okay. What you don't want to do is start trying to figure out like, oh, sort of what are the means and sort of what's going on and things along those lines. Probing these can kind of be a chore. So you just want to get a general sense in your head, kind of what's happening with stuff. Okay. Questions about this? Yes. We'll get into that and talk about that. Yeah. No, I mean, with this, I would just say there's an interactive effect of X on Y. And so then follow up with sort of the probe stuff. So there's not, I mean, you can, like, based on the coefficient, you know, particularly in, probably not for this, but in a regression model, when you're looking at linear effects of X on Y and things like that, if you've done this long enough, you can look at an interaction and sort of, and if you know how things are scaled, you can say, oh, this is what it should kind of look like, but don't even worry about that. Just focus on, we're going to go through, start to pull this thing apart and see what's happening with stuff. All right. And this is where it starts to get creative. You're going to have some decisions that are made based on your conceptualization, right? A lot of different ways to go through and start teasing things apart. Some ways will probably make more sense than others. And so before you go through and do this and just start running analyses, you want to have a good plan. How am I going to approach this based on my research question and the stuff that I'm finding in these graphs? Okay. All right. So these are line graphs, right? Easy to kind of go through and see. But if we're talking about, I like these for regression models where we're looking at linear effects or repeated measures analyses, line graphs, thing in terms of trajectories and things like that. Honestly, I prefer bar graphs just because we're looking at different groups. These are independent groups of people. Independent groups can be represented by independent bars. So here's the same. Here, right? So here, high humidity 70 or these are different, just different groups, right? But Amanda, where am I seeing sort of whether or not does this look like there's an interaction going on in this first one? No, right? The lines make it easy to go through and kind of see through, and I'm get okay. If I go through and I take a look at this right here, the bar graph simple effect, or looking at this interaction, now I'm starting to be different across my low humidity groups. Things are staying stable. Things are linearly high levels of humidity all aligned, and it's going to go through and crawl and take a look, right? Talking here about the simple effect of factor A effect at B. Here I can go through and I can say to you all. So if I look at Sam, what's the difference in performance scores between high and low humidity at 70? And what's the difference between high and low humidity at 80? 90? Okay, so what we're seeing, if we're thinking about our simple effects, right? And the simple effects is what's the difference between humidity at each level of my other factor? It's the same each time, right? Then I can also look at what's the difference between, if I'm just looking at low humidity, the difference between 70 and 80. 5. What if I'm looking at high humidity 70 and 80? 5, right? So this is just, I'm getting the same simple effect no matter sort of what combination I'm looking at. Simple effects are the differences between these individual bars here, okay? What about, I've got to see it differs across levels. What's the difference, Sam, in high and low humidity at 70? And at 80? And at 90? Yeah, so that simple effect, the comparison of those conditions at each level starts to change, right? Which is telling us that we have an interaction. So this starts to become important if we're talking about simple effects, right? We're talking about those cell comparisons. If we're talking about main effects, we're talking about row and column stuff. Okay. Yeah, Katie. Yeah. Yeah. We'll get into that. So basically, when we're going through and looking at, when we get into the calculation of our ANOVA stuff, if you have an interaction effect in there, then it tells you that by definition, you have evidence for differences in the impact of factor A on your outcome across factor B. Right? The fact that that interaction term has come up as sort of less than 0.05, sort of our interpretive benchmarks and things like that, that says, yeah, it looks like we have evidence of something different going on. Now, when you actually go through and look at your plot, if you don't have evidence of interaction, will things be as clean as this, right? But that's what we're looking at, is that interaction term, to see if we have evidence, license to move forward and start to look for some of this stuff. Okay. All right. Can or should we interpret main effects in the presence of an interpretable conditional effect? If I have an interaction, should I be interpreting main effects? No. I don't know. I think it depends on the question. Okay. Here, in this example, right, temperature, or the effect of temperature on performance, varies so greatly across these two things. So in general, you will hear that the general rule is, in the presence of an interaction, you do not interpret your main effects, right? Because they're no longer main effects, they're conditional effects. Conditional, this is just another term. Conditional means it depends on. If I have a sort of like what I would normally have and what are listed in SPSS as main effects in the presence of an interaction, throw main effects out of the window, because there is no main effect. The main effect is dependent on sort of the level of your other factor. And so by definition, it's a conditional effect. Okay. And so standard practice says, if I have an interaction, I ignore your conditional effects, what you would normally think of as main effects, and go straight to interpreting the interaction. This is probably generally sort of a reasonable idea, right? But what if I'm looking at the impact of and heart disease risk, okay? There's McKibben students who do more health psych types of things, right? So I'm looking at the relation between smoking and heart disease. And what I'm interested in is looking at this in younger versus older individuals, let's say, okay? And so what I've very strong relation there, as we would probably expect, right? But if I look, I see an increase, but it's not as dramatic, right? This seems like something that could happen in a world, right? If I'm an older individual, strong correlation between sort of how much I smoke and risk of heart disease, probably because I've been smoking for a long time. If I'm young, generally healthy, haven't been smoking for as long because of time, right? Here we have an interaction, right? The relation between smoking and heart disease risk is dependent on age, right? But if I look at sort of my overall sort of main effect, which is now a conditional effect, right? Is smoking related to heart disease? What's the answer? Yeah. And so in a situation like this, I think that's a worthwhile effect to interpret, right? Saying that, you know what, overall, in general, smoking is not good. Smoking increases your risk of heart disease. But with the caveat, what's the caveat, Josiah? Yeah, so right. Really, sort of this effect is dependent on age, right? As I get older, sort of that risk, that sort of the strength of that relationship starts to increase, right? Same thing if we're working on thinking about, Matt, you're working on sort of building, let's say, a new paradigm where you've got some manipulations that's going through. No one's really kind of done it before, but you like it, you think it's big, think that this is something that's going to be useful for lots of different research in terms of a paradigm or manipulation or things along those lines. But you want to say, like, boy, is this going to work the same across everybody, right? And in general, you find that, yes, your paradigm is effective in sort of producing whatever outcome or changing whatever outcome it is that you're wanting to do, right? With the caveat that there are certain demographics or certain groups of individuals where you see stronger effects of this and then weaker effects of this. But even with the weaker effects, they're still doing what it's supposed to do. It's just maybe not as intense as sort of other things. So you've got an interaction, right? Do you interpret that main effect? Probably worth noting, right? Saying in general, this thing does what it's supposed to. However, to expect sort of this to work the same across everybody in all situations forever and for always is probably not reasonable. So yes, it is working, but this is actually sort of like, so this is conditional on sort of the magnitude of the response is conditional on sort of these other factors that we've identified, right? Same thing, Amanda, if you're working on jury instructions, say like, yeah, it does look like sort of these instructions, if we change this up for civil versus criminal or something like that, then yes, this does increase risk of guilty outcomes if we change these instructions. However, so there are some things that sort of change how much, right? And so again, thinking about your question, what makes sense? Do I go through and interpret this here? Probably not, because there's the effect of temperature on performance depends 100% on level of humidity, right? It's a completely different effect. These other ones, like, well, I'm sort of getting the same sort of effect across levels of my other factor. It just kind of changes a little bit in terms of strength or sort of things along those lines. Okay. So that's some nuance into sort of interaction, but this is probably kind of some of the hardest concepts that we'll sort of work on here at the end. So we want to make sure you got at least kind of a headspace for some of this before we jump forward. Questions? Okay. Main effects and interactions, again, as I said before, these are independent of one another. And that's it, right? Across levels of factor A, scores decrease as we go from A1 to A2. There's no effect of factor B. B stays the same, right? Doesn't matter. Here, main effect of factor B and B. So as A, we see an increase. Do we see any interaction here, Elizabeth? We just separate these down. If we go to A1, or if we're just looking at A1, if we go to B1 to B2, how much of an increase do we get? And if we go to this, okay, so yep, take that. And if we go down here across A1 and A2, 10, 10. So we've got a main but no interaction here, right? Here, we got an A and B interaction with no main effects, right? If I'm just looking at factor A, no difference. If I'm just looking at factor B, no difference. But Basha, what's going on in these cells? Yeah, we've got a crossed effect, right? If I'm at level A, B increases. At level, or at A1, B increases. At level 2, B, we get decreases for B1 to B2, right? And Matt, if we're looking at this last example right here, what does this suggest about the benefit of these factorial designs or considering interactions? Yeah, so this last design, what does this type of effect, where we get an interaction with no main effects, of benefits of factorial designs? Yeah, yeah. What happens if because I'm like, screw factorial designs, they're hard and confusing, right? So what I'm just going to do is I'm going to look at differences in my outcome across variable B. What am I likely to find? If I just look at factor B, I just run an independent sample t-test. Do I get any effect? Yep. Yep. Because I like t-tests. Did I find an effect with my t-test? Okay, so let's say here's what happens in the universe, right? But I don't like factorial designs because they're hard and I wasn't paying attention that week in stat. And I just went through and I said, okay, I'm going to look at differences in across B1 and B2. Do I find any differences? Katie? No, because what's my score for B1 and B2? What's that? No, just yeah, 15 and 15. So I just run an independent sample t-test because I don't care. I'm just going to look at factor B independently. Do I find any effects? Nope. And say, okay, well, maybe factor A is where it's at. So I go through and I run a new study and just look at factor A, right? Do I get any differences there across those two? No. So I go through and what I say is that factor A and factor B, nothing to see here. There's nothing going on, right? No reason to move forward. Is that a good conclusion to make sort of based on what I've got? No, right? Because what's happening is there's an interaction. These two depend on one another. If I just look at B in isolation, I'm not going to find anything. If I just look at A in isolation, I'm not going to find anything. And so then I say, well, moving on to a different area, when in fact, there's a very big effect there, right? Essentially, we've got design saying, right. So my performance on A and B, it's just the combination. And if I miss one of the combination with the other stuff, this starts to become important when we start thinking about moving into more complex designs. There's more assumptions, there's more things going on, but also study in psychology by one thing, right? And or the effect between A and B scenarios. This is where we start to get, it starts to become important that we start thinking about our theory. How do we understand things to go through and sort of work together? What are reasonable variables that I can go through and look at with this and start developing research questions that are interesting, informative, and have to be going through everything, because we can't have think about on a small. How do I go through and tease this out? What are the other things that are okay? All right. Are we excited about factorial designs? Good, right? So, all right, what we've got here is we got again, if we're talking about a two-factor ANOVA, we've got three separate omnibus effects. Okay, each one of these has its own hypotheses, own tests. So we've got a main effect of factor A, main effect of factor B, and an interaction of A and B. Okay. Now, again, in the presence of an interaction, these are no longer main effects. What are they? Conditional effects. Okay. Because I can no longer tell you what the effective factor A is on outcome. I can tell you what the average effective factor A is on outcome, but I can't tell you specifically what it is because it depends on factor B. Same thing here. In the presence of an interaction, this is no longer a main effect. It's a conditional effect. I can look at this, interpret this as on average what happens as we look at different levels of factor B, but really what's happening is it's dependent on factor A, right? And then we've got our interaction. Again, anytime you say here something has an interaction, it's saying, oh, well, the relationship between X and Y is dependent on some other variable, right? If you say that, you will always be right because that's by definition what these interaction terms mean, okay? And start to become really cool ideas for papers and theses and dissertations and things along those lines, right? Because main effects will only take us so far, right? And probably never actually represent what goes on in the universe, right? So starting to think about what are the types of things that maybe change the nature of these, the associations between these variables, okay? So as we start to think about calculating our two-factor ANOVA, okay? Again, thinking about how we went through and started to partition out variability into within, between stuff. You all are working on that right now. Having you do that in problem 1 in this set, right? You have to go through and kind of figure out and know what you're looking for and how to calculate it and sort of reverse engineer figures to go through and populate that table, right? Starting out with total variability, this is all the variability in our scores, sort of all my outcome, right? In whatever I'm measuring as my outcome, this is all the variability that's going on in there, okay? What we're gonna do is we're gonna split that into 2 different parts. Again, we're gonna split it into our between and our within. Sam, what's our within treatment variability or within effect or within variability represent? It's error, right? Because it's stuff that we haven't accounted for. It's a combination of systematic effects, random effects, who knows what else, right? But it's not anything that we've modeled. And if it's not something we've modeled in our design, then it is by definition error, okay? What about our between treatment variability? Matt, what's our between treatment variability represent? Yep, the differences that we're seeing across our different conditions, right? What we're going to do here then, though, with our factorial design is with our two-factor design, is we're going to take that between pot and we're going to split it into specific effects. We're going to have between groups variability or between treatment variability that's attributable to factor A, stuff that's attributable to factor B, and then the interaction of those 2 things, okay? So again, if we're thinking about overall conceptually what's going on, starting with our total piece of the pie, split it into error within the stuff that's going on within cells, and then we've got our between group stuff, right? Same as we did with our one-way ANOVA, and then we're going to take that between, and then we're going to start factoring it down into specific effects here. Okay, so table set up the same way, really nice because everything sums to 0, everything fits nicely and is in its place. So all we need to do now is go through and start populating this table here. Okay, so what we're going to start out with again is our sum of scores total. Okay, this is our total variability for the entire set of scores. So if you went through and were to just calculate the variance of Basha, what are we measuring? What's our outcome here? Depression. All right. If we're just measuring our depression scores, this is just all the variability in our depression scores. It's just all the stuff that there is. This is the total piece of the pie that there is no more variability than if we just run the variability on this column of scores, or the variance on this column of scores. That's all this is, right? Now, from an ANOVA design, we can start to think about this more carefully as our sum of squares total being the sum of the squared deviations of person K at level I of factor A and level J of factor B. So again, this is a two-factor ANOVA. So our notation gets a little bit more involved. So we've got individual I, excuse me, The I is like, never mind. Okay. So we've got person K who is in group I of factor A and group J of factor B. This is identifying our specific cell. Okay. So this is each individual person, regardless of their group minus the grand mean. If we sum those squared deviations, that's just all the variability in the total set, with tracks with just calculating variability with across individual like we would normally, right? It's just all the sum of the squared deviations of all scores from the sample mean, sum that up, and so then going through and doing that, that's all this is here. Okay. Now, sum of squares total, we can also get this by calculation. Have well, somewhere I give you that handout that has sample data. Here it is. Okay. This handout here, right? So basically, if I were to go through and take the grand, the sum of my squared x values minus the square of my grand mean over the total, all the people in the data set, this would give me a different way to calculate my sum of squares total. Okay. Again, all variability in the sample. What we're going to do is split this into between and within. Degrees of freedom for our sum of squares total is one less than the total number of scores in my set. Okay. So again, this all tracks, if you think back to how we calculated variance in some of those very first lectures, it was just taking the sum of the squared deviations of all the scores in the set, dividing it by sort of degrees of freedom. Like by the time I can choose whatever scores I want for those people until I get down to the last one. And then because that's the sum of those deviation scores have to be to 0, I've lost a degree of freedom here, right? So this is just calculating. The total is just the total variance of the full set here, or the full sum of squares. Okay, so sum of squares total based on this here is just 840, right? The sum of our squared x's minus 120 squared over 30. Degrees of freedom, there's 30 people in this example, minus 1, right? And then we can go through and just start populating our table here. Okay. People okay conceptually with sum of squares total? Okay. All right, now our sum of squares error. Okay, sum of squares error, this is just variability within each condition or group. Okay, we're going to calculate this by, so we're taking the sum of the squared deviations of person K for at level I of factor A and level J of factor B from their respective cell mean. Okay, so basically what we're doing, if we take a look at this handout here, I'm taking, if I start up here with a person in the easy low group, right? I'm taking 3 minus 3 squared, 1 minus 3 squared, 1 minus 3 squared, 6 minus 4 squared, 4 minus 3 squared. Then move over 2 minus 6 squared, 5 minus 6 squared. Basically, it's just the squared deviations of each individual from their group mean, their cell mean. Okay, and this is consistent with what we've talked about as error, right? Because Basha in this output, right? So I'm looking at the difference. So in this example, I guess I should have set this up. What we're doing is we're looking at the impact of both task difficulty and we'll say sort of cognitive physiological arousal on performance, let's say. Okay, and so we've got easy versus hard tasks, and then we've got low arousal, medium arousal, high levels arousal. Okay, so how many distinct populations do we have here, Basha? How many? How many distinct populations in this 2x3 design? 6, right? We've got low easy, medium easy, high easy. We've got low hard, medium hard, and high hard, right? So we've got 6 distinct populations that we're looking at here, right? And so what we're doing is we're just adding up the sum of the squared deviations of each individual from their group mean, right? Because Amanda, if the only thing that impacted performance, like, and in a deterministic world where performance was 100% the result of task difficulty and arousal level, what should everybody in each one of these cells scores be? They would be all the same, right? But they're not all the same. They'll never be all the same because we have error, right? So there's other stuff going on that's impacting performance that we don't know about because we haven't measured. And if we haven't measured it, then it is by definition error, okay? So again, sum of squares error, same thing as before in the previous. We're just looking at sort of aggregating people's individuals' deviations from their respective cell means. As those scores get bigger and bigger and people start to get sort of more variable within their cells, we've got more variability. As it becomes less, we got less variability, right? So same thing as we were doing before. We can also calculate our sum of squares error as we can just sum the sum of squares per group, right? So I could go down through and take the sum of squares for each group and add those up. That gets me there. I can also get there by subtraction. If I go take the sum of squares total, which we've already calculated, subtract sum of squares cells, which we haven't calculated yet, this will give me sum of squares error as well, okay? So again, just playing around with this. And again, this is all the variability within our cells due to individual differences, experimental error, and things that we haven't measured, right? Degrees of freedom is going to be the product of levels of factor A, factor B, and the number of participants minus 1. So degrees of freedom error here is going to be number of levels of A, number times number of levels of B, times the number of people we have per cell minus 1. This works fine if we've got a balanced design. If not, then it starts to get tricky. We can also calculate degrees of freedom error by subtraction. We can take degree of freedom total minus A, degrees of freedom A, degrees of freedom B, minus the interaction degrees of freedom, and get there as well. Okay. So again, talking about sum squares error as the sum of the sum of squares for each group, right? So if I go through and look at my sheet and I add up all the sum of squares, that'll get me there, okay? Degrees of freedom, number of levels of factor A times the number of levels of factor B times the number of people per cell minus 1, 2 times 3 times, we got 5 people per cell, so 4 there. That gives us our within treatments or our sum of squares within our sum of squares error, whatever you want to call it, that sort of populates that there. People with me so far? Okay. Now, sum of squares factor A. This is the variability due to differences across levels of factor A, okay? Think about this in our example. These are our column or our row differences that we're seeing. So what we're doing to calculate this, so sum of squares for factor A is the sum of deviations of the mean level I of factor A from the grand mean multiplied by the cell n and the levels of factor B, okay? So to calculate this, I take number of people per cell, assuming balanced design, times the number of people or the number of levels of factor B. And then to calculate this is easy. I'm just going to take the mean of level I of factor A minus the grand mean and square that up, okay? So if I'm looking at my output here, what I'm going to do is, so for factor A, I'm going to go through and I'm going to take a look at, so the grand mean for factor A is going to be 6. So A, sort of easy, so that's A1. A2 is hard, that has a mean of 2. Basically subtracting those means from the grand mean and then multiplying it by squaring that, multiplying it by other stuff. So that gets us there. Basically, we're just looking at the difference across our levels of our factor, ignoring the other factor there, okay? We can also get this by taking the sum of the row total, the square of the row total over the number of people in each row, minus the grand total squared over n. Mathematically, they're equivalent. This is just often easier to do it, but wanting to make sure that you understand by definition how these are being calculated, and the degrees of freedom is just one less than the number of levels of factor A. Okay. So here, if we do this, we see the row total for A1 is 90. The row total for A2 is 30, right? So we just take those, square those, divided by the number of people, square those divided by the number of people, minus the grand total over the total number of people. That gives us our sum of squares A. This is handy calculation. This doesn't mean anything. I can't look at this and sort of say, oh yeah, this is conceptually what's happening. That I can, right? So just sort of wanting to know the difference between the two, right? Two levels of factor A minus 1, drop that down. And so we get sum of squares for factor A, 120, and degrees of freedom 1, okay? And then the same thing for factor B. We're just going, yep. That's total. That's total. So Emily, if you were to go through and calculate, and you have this worksheet up, if you were to add 15 plus 30 plus 45, it gives you 90. It's just the total scores. Okay. We're just playing with algebra here. Okay. And then the same thing for factor B. Nothing interesting or unique or fun going on here. We're just taking the looking at the sum of the square deviations of mean level J of factor B from the grand mean multiplied by the number of people in each cell and the number levels of factor A. So again, here, if we think about arousal as our factor B, all right, we've just got 2 minus the grand mean, 5 minus the grand mean, 3 minus the grand mean, square each one of those deviations, sum those up, multiply it by the number of levels of factor A times the number of people per cell, and that gives us the variability that we're seeing across our means at each low, medium, and high levels. Okay, degrees of freedom, again, just the number of levels of factor B minus 1. So again, if we take the shortcut here and just take the row total squared over the number of people per at that level, same thing for medium, same thing for high, minus the grand total squared over n. Degrees of freedom, we got 3 levels of factor B, minus 1 is 2, and we can just populate that in there. Okay. All right, let's go through and stop there. I think that's a good pause point, so to go through and take a break. So again, with this, what we've done up to this point is no different than what we were doing before with our overall ANOVA. It's just basically like we ran 2 sum of squares between for our ANOVA, one for one factor, ignoring across the other factor, another for the other factor, ignoring across the other factor. All we've done here to this point is we've calculated the total variability in the scores. That's our total piece of pie, right? We've calculated the within cells variability. So that's this variability. These are differences in scores that we can't account for anything because it's not a measured factor in our model. And so getting a sense of that, and again, that's going to be the denominator of our test. This gives us a sense for, okay, if things are just moving around at random or because of things that we haven't measured, what would we expect, right? And then we've gone through and looked at across group differences, sort of mean level differences across levels of factor A, across levels of factor B, just like we did with our ANOVA previously. These are just sort of different betweens. And then, so everything up to this point is conceptually similar and analogous to what we've done before. So just to try and sort of set that in your head with stuff. Okay, awesome. All right, let's go through. We'll take 10 minutes, come back at, a little before 1:45. Yeah. All right. So, got our main effect stuff, and that's basically what we were sort of working on. ANOVAs. What we're going to do now is going to go through and pull out what we're going to call sum of squares cells. Okay. This is kind of a computational variance estimate that will become relevant sort of at some point. Not typically something that's included in our standard ANOVA tables, although in SPSS, if you're looking at your ANOVA table for your factorial design, you'll see a corrected model sum of squares. That's just the sum of squares cell that's sort of going in, but it's not something that's traditionally included in there. Again, kind of conceptually similar to sum of squares between that we counted are one way. Sum of squares cells gets variability associated with systematic differences across factor A, factor B, and then the interaction, the combination of that. Okay, and so basically how we're calculating sum of squares cells here is just going to be looking at the sum of the squared deviations of level I of factor A combined with level J of factor B from the grand mean multiplied by the cell size. So basically what we're just doing here is we're taking each one of the cell means, subtracting it from the grand mean, squaring that deviation score. And so basically this is just looking at, if you took each one of those individual cells and ran it all as a one-way ANOVA, that would just be the differences across these. Okay, so we're just looking at the total differences across sort of these individual cells here. We can also get this by subtraction. We can take sum of squares total minus sum of squares error, and that's going to give us sum of squares cells as well. Okay. People see what we've got going on with this computational figure here. Ish. Okay. We're just looking at total variability across our individual cells. So sum of squares cells is going to be sum of squares total minus sum of squares error, 120 or 360 minus 120 is going to give us sort of our value there for that. Again, this isn't something that goes into the table, but it's something going on in the background. Okay. All right. And so for our two-factor ANOVA, what we're going to have is a sum of squares for the combination of A, B. Okay. And what we're going to do is we're going to get this by subtraction. The sum of squares A, B this is the variability of the combined factors A and B. This is the unique effect of the combination of these two outside of what's uniquely attributable to factor A and what's uniquely attributable to factor B. So our sum of squares AB, this is going to be the cells minus sum of squares A minus sum of squares B. Okay, and we always get this by subtraction. Degrees of freedom is just going to be the degrees of freedom A times the degrees of freedom B. And again, if we're tracking and keeping track of where this is all coming from, we've got our total variability. We've calculated our within, so we sectioned that off. We've got between, this is our sum of squares cells. We've got factor A, factor B already calculated. And so the only thing that's left over is this interaction. So anything that's not accounted for in the between, the sum of squares cells, that's not attributable to A and B is just due to this interaction factor here. So again, sum of squares cells for the two, or sum of squares AB for the two-factor design is just our cells minus A minus B. That's 240 that we calculated for cells minus 120 minus 60. And then we've got our degrees of freedom for the interaction is the product of 1 times 2. So we've got that there. And we've populated our design, our sum of squares for this. Okay. Do people kind of get a general sense or tracking kind of how we're partitioning this variability and conceptually what these different components sort of correspond to? Yeah, Emily. Yep. And that's just the degrees of freedom for your interaction. Okay. All right. So our sum of squares, then right, because we need to do squared is we just take our sum of squares divided by our degrees of freedom, gives us a mean squared within. We go through calculate sum of squares for factor A, or excuse me, take the sum of squares for factor A divided by our degrees of freedom, get our mean squared for factor A. And in ANOVA talk, what is a mean squared equal to, or what does a mean squared represent? Yes. Well, Basha, what did you say? So one of them does, but if I just say mean squared, what does that mean? What is it? Yes. Did you say variance? Amanda said variance. Okay. Yes, exactly. Variance, right? So what we've got is just a variance estimate. Mean squared is just ANOVA talk for variance. like all the variance, pooled variance, sort of sample variance, all the variance. We just call it mean squared in ANOVA talk. So we've got our sum of squares divided by our degrees of freedom gives us a variance estimate. And if we take a variance that we're seeing across levels of factor A divided by the error that we would expect if the null hypotheses were true, or just that things were happening at random. And what do we get, Katie? If we take a between divided by within, what does that give us? In terms of our test statistics. Not your interaction. My F test, right? Again, so thinking about F as being a ratio of the difference that I'm seeing across, right? Divided by the differences that I'm seeing within, and so the variability across my groups versus my variability within. This is just the stuff that's going on within is just, this is my guesstimate. If everything's completely random and sort of there is no effective A or B or any other interaction, then the differences that I would see across my levels is about what I would see within my levels. But if I'm seeing more differences across my levels than what I'm seeing doing just within on aggregate within my levels, then that's something I'm going to say is, oh, it looks like there's maybe something systematic there. So I take my mean squared for my factor A divided by within, and I get my F. Okay. Same thing for factor B, within divided by, or excuse me, my between divided by within, get my F for my interaction. So to get my mean squared here divided by within, get my F. So I get 3 F tests with this. Each one of these F tests correspond to a different effect and correspond to a corresponding to a different effect, corresponding to a different hypothesis. Okay. We'll see how we went through and sort of added all that up. Okay. And so nice thing is before this adds, this squares, these sort of the mean squares don't, but these all sum up so that everything comes up the same with stuff. Okay. All right. So what we end up here, and if we were to go through and take a look at compare these with a critical F with 120 and 5 degrees of freedom, or excuse me, 1 and 24 degrees of freedom here. Compare 6 with a critical F of 2 and 24 and a critical F of 2 and 24. That would be our comparisons across here. And then we can go through, or we can just go through and sort of look at a p-value for an F with 1 and 24 degrees of freedom, F of 6 with 2 and 24, F of 6 and 2 and 24, get a p-value with that. Okay. We've got 3 statistically interpretable effects. We've got effective task A, telling us that we have differences across difficult versus easy tasks in terms of performance. We get a significant main effective B, because we're seeing sort of systematic differences across levels of arousal. And then we get a significant interaction of A times B. This is saying that the influence of arousal and task difficulty are interdependent. Okay. And in this case, what we would generally do is ignore our main effects and go directly to our interaction. Okay. Now we can go through and think about, does it make sense to make a comment on those main effects? But at this point, in the presence of an interaction, do we have main effects? Nope, we just have conditional effects, right? And so we probably, in this case, probably wouldn't go through and talk about that. We'd probably just go through and talk about the interaction, okay? And again, like I said before with that bullet, anytime we see an interaction, we're just saying that the effect of arousal on performance is conditioned on task difficulty. Condition just means dependent, right? And you could say the effect of arousal on performance depends on task difficulty. We could flip it around. We could say the impact of task difficulty on performance depends on arousal. So we can go back and forth with this. Yeah, Emily. So this is the thing, part of this is terminology, right? And it took me forever to kind of figure this out. Like mean squared, that sounds crazy and weird. What is that? It's a random number. It's just a variance estimate, right? Condition, what does that mean? It just means dependent, right? Variability, what does that mean? It just means differences, right? So sort of understanding conceptually what's going on, I think starts to become very important, because then it makes it feel like these things aren't just coming out of nowhere at random, right? So again, what did I say? Anytime we get an interaction, first thing we go through and do is plot it, right? And if we go through and plot this, we see a linear increase in performance, or linear increase in performance at low levels of arousal, right? Or excuse me, for easy tasks, right? If I'm looking at easy tasks, as my arousal level gets increased, so my performance increases. So Basha, what does this tell me about the effect of physiological sort of emotional arousal on performance for easy tasks? What's that? Okay, so if I get an easy task, right, and I start and I'm at low levels of sort of activation, I'm like just woke up, my performance probably isn't going to be good. I start to wake up a little bit more, it's a little bit better. If I'm really alert and sort of maybe even over alert a little bit, I've had too much coffee. If I got easy stuff to do, it looks like that increases. Okay. What about if I'm talking about difficult tasks? Now what happens, Sam? Okay, so overall, if I'm sort of collapsing across it, I'm saying people are performing lower at more difficult tasks, right? So that makes some sense, right? But what's the specific effect of arousal level at high task difficulty? Right. Yeah. Yeah.
But if you're under aroused.
Exactly, right? So we're getting a different pattern of effects depending on for the relation of arousal on performance, depending on if we're talking about easier or easy tasks or difficult tasks, which kind of makes some sense conceptually, right? And if we're looking at our simple effects, right? If we're looking at the difference between easy and difficult tasks, if we're looking at differences in performance across easy and difficult tasks at low level arousal, is different than medium levels of arousal and is very different at high levels of arousal. Correspondingly, if we go the other way, if we look at sort of the impact of at easy, sort of here, between low and medium, low and high, medium and high, that's a different effect than if I'm looking at differences across arousal at difficult tasks, right? So we've got, if we go through and create our lines, we've got completely different patterns going on here, suggesting an interaction, okay? So Amanda, if I were to say, if I were to ask you, hey, Amanda, what is the impact of physiological activation on performance on whatever task we're talking about? What are you going to say? It depends on whether or not we're talking about higher, easier, difficult tasks. Very much so in this, right? So people kind of getting this sort of the nature of these interactions and kind of what they're looking like here. Okay, cool. So this is just a structural model. We won't worry about that because we won't need to worry. But basically, sort of this is just identifying this ANOVA model that we just looked at is just a special case of regression. Any analyses that we could run within this ANOVA design, we can also replicate within the terms of the context of a regression model. And this is just kind of setting some of this stuff up. Okay. Yeah. It's always the case. Yeah. Yep. And this is why we start working out this semester in means-based designs, because it's kind of that classic experimental design that maps onto a lot of the types of stuff that we do for theses and things along those lines. Next semester, we're going to get into regression, and this is just basically our most basic form of our generalized linear model. And it's just a more flexible approach. Basically, these were kind of developed separately, but mathematically they're equivalent. And if we recognize that, we can start to go through and do some more interesting stuff, start to use estimators that account for some of the violations that are hard to account for if we're just running a straight up sort of traditional ANOVA design. So it just gives us some more flexibility. Okay. All right. So another thing to think about is think about in terms of power. One of the things we see is that our factorial designs are often more powerful than our individual one-way designs. Okay. And where this addition starts to come from is we start to account for more variability in our dependent variable as we start to add in different factors. We can think about these other things that we're sort of loading in there as kind of like covariates. Okay. Because Sam, what goes in the denominator of all of our F statistics here? In the denominator, the within, right? And in that within, that's all the stuff that's variability that's attributable to stuff that's we haven't accounted for in our model, right? And so let's say that we've got a study looking at self-reported arousal, calm to excited, in response to, let's say, a fear, amusement, and anger eliciting film stimuli. We're doing some emotion research, right? And we want to see how people are responding in terms of excitement to these three films, right? If we go through and we just run this in our straight up ANOVA, right? We just got a one-way ANOVA. We got film as our independent variable. So we got 3 levels of our outcome, or 3 levels of our IV. Our emotional arousal is our outcome. What we're going to do is we're going to take the total variability that we're seeing across scores, and we're going to split that into variability that's due to our film condition and everything else. Doesn't matter what it is, but everything else goes into that error term. Okay. And so if I go through and I calculate that F statistic, sort of anything that's not related to systematic variability in self-reported arousal is going to be due to this error term. Okay. Now let's say we have a different study here, right? And here we're going to go through and we're going to again look at emotional arousal in response to fear, anger, and amusement eliciting stimuli. But here, let's say that we hypothesize that participant sex, that men and women may respond to this film differently. Okay. And so what I'm going to do is I'm going to go through, I'm going to take the total variability, I'm going to have variability to do the systematic differences, but this time I'm going to have film, participant sex, and then the interaction. Okay. And then everything that's not due to that gets chalked up into my error term. Okay. So Teresa, why am I getting more power on average probably in this study based on some assumptions as opposed to study 1? Yep, I've gone through and I've modeled it. Now, if sex and the interaction of condition and sex has nothing to do with responses to the film, do I have a more powerful study? If my effect has nothing to do with sex or interaction. Yeah, kind of is a little bit of a trick question. Technically, theoretically, if sex and the interaction of condition and sex has absolutely nothing to do with response to this film, then technically these two terms should be 0 and my error is the same. But this is sort of the classic ANCOVA approach, right? Where I'm going through and I'm sort of having things that I think are just going to be nuisance variables, things I don't think are necessarily going to be systematically related to my my other IVs or things like that. It's just kind of pulling up because there's always going to be some sort of random stuff sort of going on, and it's just shrinking this error term. But if there is some systematic difference that's due to participant sex and maybe unique differences in how people report responding to fear versus amusement versus anger-related stimuli, then all of a sudden what happens is it shrinks that error term down. And now all of a sudden that error term is smaller, right? And if I have a smaller denominator in my F statistic, Josiah, what happens to my F ratio? Yeah. Yeah, it's increasing. I'm sort of reducing the noise in my model. I'm sort of having sort of less things that are unaccounted for. And so as a consequence, my power is in general going to increase with this. Okay. Now, this isn't to say that for all studies, throw all possible variables in there. That's bad for other reasons. But in general, if we're thinking about our one-way designs versus our factorial designs are probably on average going to be more powerful. Okay. You kind of understand so the logic behind this. Okay. So for our effect sizes, we continue on, we get into more sort of complicated sort of variations with things. For my effect sizes, I can still calculate my eta squared. This is easy peasy. This is my sum of squares effect over my sum of squares total. And again, this is the total variance attributable in effect for this sample. Again, remembering that eta squared is positively biased, so we want to be careful with that. And so the problem that we run into with our eta squared in a factorial design is what's going to typically happen is our eta squared value is going to start to get smaller the more factors that we have in there, right? Because remember that in psychology, everything's kind of related to everything else. The sum of squares effect that we see up here is the sum of squares that's going to be uniquely attributable to this thing, right? And if so, I have one factor that's kind of related to another factor. Now, if you're doing straight up experimental stuff, right, and everybody's randomized, then those factors should be orthogonal to one another. But if I'm running studies where I'm sort of basing groups on pre-existing differences, a lot of times those pre-existing differences will be related to each other to some extent. And so as I start adding in other factors, this sum of squares effect starts to get smaller and smaller because the sum of squares effect that we're getting here is stuff that's unique to that factor and nothing else, right? And so what happens is that if I run a one-way ANOVA for, say, my impact of temperature on performance, 70, 80, 90, and I run a one-way, I run a one-way ANOVA, and then I sort of run a sort of 2x3 where I'm looking at humidity and temperature, and I still have that sum of squares effect for temperature. That sum of squares for temperature is probably going to be smaller than it was for the one-way. And so what ends up happening is it makes it hard to start comparing this eta squared statistic across designs, right? So even though we can calculate eta squared for our factorial designs, the concern is that this is an effect size. If I'm in a factorial design, I'm expecting my eta squared to be systematically smaller than if I'm looking at one-way designs. And so then there's some concerns about how I go through and use that. So same interpretive standards for small, medium, large as before. Same interpretation for eta squared as before. The problem is just thinking about if Matt runs a study looking at some factor, and Josiah then goes through and sort of wants to sort of runs a different study with a different design, concerns that this eta squared statistic in terms of effect size may not be comparable across because Matt took a different approach than Josiah did. Okay. And so what we have then, and what you'll typically see as the effect size reported for factorial ANOVA is a partial eta squared. Okay. Partial eta squared is calculated as the sum of squares effect divided by the sum of squares effect plus your sum of squares error. Okay. Now what's missing relative to the sum of squares total, eta squared, this is just the effect, the differences that I'm seeing due to my factor over all the whole piece of the pie. Okay. Partial eta squared is the sum of the squares, the differences I'm seeing for this effect over the differences I'm seeing for this effect plus my error term. What's missing from the denominator of this relative to the sum of squares than our calculation for our eta squared? If we've got, say, a two-way factorial design. Yeah. A and B and what else? The interaction, right? So our denominator here is going to be smaller. That denominator is going to be systematically smaller because what we're looking at with our partial eta squared is what I would how I would phrase it is the proportion of residual variance unaccounted for by other factors. Okay. So if I go through, and if we think about sort of what's going on in this denominator, if I take total piece of the pie, So this is all the variability, right? This is the denominator in our eta squared. But if I am going through and taking a look at my partial eta squared, let's say this slice of the pie is due to B, and this pie is A times B, right? What I have left over, if I pull out variability that's not accounted for by other factors, what I have over is all of this, right? And now, if I go, this is attributable to factor A, right? What I'm doing is I'm saying of all the stuff that's not accounted for by other variables or other effects in my model, if I take the other knowns out and set those aside, of what's left over, right? Of the residual variability here, of the residual variance that's left over after we pull this stuff out, what proportion of that is attributable, uniquely attributable to factor A? So it's a little bit more of a tricky, we're talking about in terms of denominator. What eta squared is really nice because it's saying total piece of the pie of everything that we're seeing, what's uniquely attributable in this design to sort of my effect. Partial eta squared, a little bit more tricky. We're saying if we take out everything that's related to other things, right? Now what's tricky about that is I don't know how much is related to other things, right? And so this could be a big piece, a small piece, who knows what's left over. But of what's left over, of variability that's not accounted for by other factors, of that, what's attributable to my effect. This is our, and what's nice about this is one, it's central for the calculation of power. We'll go through and use that to calculate F statistics and, or F's not big F statistics, small F statistics. But what it does is it goes through and lets us calculate power. And what it does is it lets us go through and provides a more comparable effect across different studies. So Basha, if you went through and you ran, say, a 2x2 factorial design, look at some outcome. And Teresa, you went through and you did a 2x2x3. So you added in an extra factor. And what you're interested in saying, looking at the effect that you found of factor A and the effect of Basha found of factor A, eta squared is hard to compare because there's sort of eta squared for your studies are going to be systematically smaller than Basha's just because you had an extra factor in there. It takes other things into account, right? But what we could look at partial eta squared and so make a more direct comparison across this. Okay, so these partial statistics are kind of tricky to wrap your head around. We're going to get into these a ton when we get into regression analyses. But do people kind of understand, see where these partial eta squared is when we're talking about residual variance, unaccounted for by other factors? People kind of seeing that pie graph is a good way to think about this. Questions? Yes. Then, Katie, that's a good question. So let's say I calculate partial eta squared for a one-way design. What do I end up with? So let's say we've got a one-way ANOVA. So I've got my sum of squared effect. And I sort of take that over sum of squares effect plus sum of squares error. What essentially am I talking about in the denominator then if I've just got a one-way design? Yeah. Partial eta squared reduces down to eta squared in a one-way design. That's why we can't calculate partial eta squared with a one-way design, because there's nothing to control for, because we've only got one factor in there. Okay, and so you're exactly right. Sort of for partial eta squared or for eta squared, this is just if I take my effect and my error, that's everything I've got. But when we look at our factorial designs, that's when we now have other things. So we say, okay, if we suck out stuff that's due to, say, participant sex and task difficulty, and we're only interested in arousal, so what's left over, how much of that is uniquely attributable to arousal, and that's where we get our partial eta squared. Yep. Again, sort of less meaningful conceptually, right? A total piece of all of it is a pretty easy thing to communicate, right? Sort of the proportion of what's left over is hard to kind of wrap our head around, but generally ends up being a sort of more useful statistic. And you can still calculate. So you can't calculate partial eta squared for a one-way design because it's just the same thing. You can calculate eta squared for a factorial design if you want to, and if it's important. It's just trouble comparing that effect size across other studies that might have different designs or different factors. Okay, so F statistic, this is our statistic used to calculate power, is just a straight association with partial eta squared. We can move back and forth in terms of calculating that. F statistic, small, medium, and large. Again, F doesn't have any real good practical interpretation, but it is the formal effect size for calculating power. So just knowing that association. Okay. All right. So just like eta squared, partial eta squared is a positively biased statistic or a positively biased estimator of the population effect. Okay. And so what again we have, just like we had omega squared as a population-based estimate of eta squared, we have partial omega squared that we can calculate based on, that gives us a sort of better population effect of the residual proportion or the percentage of residual variance that's not accounted for, that's attributable to the factor, sort of based on the population. So basically all the same stuff here. Now the tricky thing about omega squared, partial omega squared, as before, our omega squared statistic assumes that we've got a balanced or nearly balanced design. If you don't have a balanced or nearly balanced design, it's hard to justify sort of putting that out there. Just PS, knowing that it's likely an overestimate of the actual population effect. When we get into or partial omega squared, other complication that comes into this is that it the calculation squared is the design. The calculation sort of, if you look at various tricky. Now, if you need to calculate a good general formula for eta squared and partial eta squared, okay, and I think SPS still take a look. But if we wanted to go through, calculate in a factorial design, wanted to calculate omega squared or partial omega squared, these are general formula that will go through and get you there. Okay, but again, the interpretation same as before, right? This is just a better population-based estimate for this omnibus effect than what we get with effect size. Again, pretty easy, straightforward. We go through, get upper and lower non-centrality parameters for using our online calculator, drop in our F value, eta squared, partial eta squared statistics that we typically calculate at 90%. Because we can't have a lower bound really, because it's not a symmetrical distribution. And so what we do is we just calculate at 90% and sort of put all that in the one tail there. But again, the formula for that is pretty straightforward. And so sort of summarizing effects, and I posted that of my notes through and sort through this stuff and sort of get a sense for what this literature looks like. If we're talking about eta squared and omega squared, proportion of variability a total attributable factor. Sort of our components are all going to sum up to 1 because we're talking about the total piece of the pie. And for our factorial designs, I think because we know that eta squared is positively biased. But if I'm looking at across designs, eta squared for a one-way or a factorial design will be systematically lower than the same eta squared for a one-way design. So trying to think about sort of how this works out, right? So what we typically will report in our factorial designs are partial coefficients. So we've got partial eta squared, partial omega squared. This is looking at the proportion of residual variability in our outcome. The residual proportion of residual variability in our outcome that's attributable after we partial out stuff due to other factors, right? So we take that out, and now we've got a new pie that we're talking about. It's a smaller pie of the smaller pie of unexplained stuff. How much of that is due to my factor? Okay. Again, useful for manipulation of asterisk. As soon as we get into repeated measures designs, we get into repeated measures ANOVA stuff like that we'll work on next semester. Now all of a sudden we've got kind of a different wrinkle that comes in with there. But for our between factor stuff, this is generally what we would do. And then again, these are generally what we're using to calculate estimates of power. And again, in G-power, tests, if we go to ANOVA, fixed effects, special and main effects and interactions, that's just our factorial design. A priori power, we can go through and hit determine to get our F. You can enter that directly, or you can on just dropping a partial eta squared in there, okay, and then just transfer it over. Here's degrees of freedom, main effect interaction. So you just remember how to go through and calculate that piece. But if you just have a partial eta squared, you can just drop that in, and it just calculates it automatically. Okay, how are we feeling about this? It's a lot. Should have hit a lot of material. Okay, and this is all kind of conceptual stuff. Any questions? Okay, let's jump into SPSS stuff. So open up that file. Okay, I've got training. All right. And the factorial data set that we have loaded up, the 2x2 ANOVA, or the 2x2 ANOVA for expressive behavior. And so what we're interested here is looking at, and then you can pull up the screening handout too if you want to follow along with that. What we're looking at is the impact of expressive regulation on physiological activation, subjective response to different films. Okay, so what we're asking people to do is view one of two affectively valence films. We're either going to show people a sad film or a humor film under instructions to either inhibit the expression of emotion or watch the film naturally. Okay, so again, my apologies in advance for, I don't know, is this helpful or not helpful? So like the idea is like using kind of the same idea and sort of example sets from, so that there's at least some kind of consistency and you kind of understand, is this a helpful thing, or are you tired of thinking about films? Okay. It's also a nice thing because it's something that's not necessarily related to PTSD and trauma and clinical stuff to sort of spread the stuff around. So, okay, good. So design here, what we're going to do is we're going to give people, randomize people to one or two different films. Humor film, sadness film, under instructions to either watch the film naturally or inhibit. And what we're going to do is we're going to, before we sort of go through, we're doing a little bit of pilot here. And what we want to do is we go through and we record all these sessions as people are reviewing and have an external coder rate overall level of expression on a 1 to 5 scale. Okay, so people are going through watching their random assigned film under instruction to inhibit or express, and then we're just having people watch and record and externally code. Okay, and so what we expect is that researchers, if my manipulation is working right, if people are actually, if I tell people to inhibit expression, hopefully what I'm seeing is that people will show lower levels of observable behavior. So while they're watching these films, but kind of the wild card here is I don't know if we're going to get equal levels of expression across the humor and sadness film and sort of what that interaction is doing. So what I'm going to do is I'm going to go through and run this pilot as a 2x2 ANOVA design where I'm sort of including film condition as a factor, instruction condition as a factor, and then my outcome is just observed expression based on an external coder. Okay. So what we're going to do to start, we're going to start by doing some screening. Okay. So if we open up SPSS, right? I'm going to walk through and take a look. And first thing I'm going to do is I'm going to just go through and sort. Okay, so it looks like I have 3 variables here, or 3 cases here where I'm missing data, right? So I'm going to go through and get rid of that. But if we first go down through and take a look at my variable view, so we'll say, looks like we've got our participant number, film condition, sadness, amusement, instruction condition, express, withhold. And then I've got this other condition here, sad express, sad inhibit, humor express, humor inhibit. What's that about? Yeah, Emily? No, because we're just having sort of people go through and take a look, right? And sort of just watch the film. Elizabeth, what are you seeing? Yeah. Yeah. What this is an indicator variable that's identifying my individual cells. Okay, and this is going to be important when we go through and we start screening because, okay, Basha, when we were going through and screening for our one-way ANOVA, what did we have to do before we started looking at distributions and things along those lines in our screening? Yeah, what did we, can I just look at skew kurtosis distribution for everybody in the set with my ANOVA model? Nope, I got to look at it separately across groups, right? But now when we get our factorial design, right, I've got different groups for film condition and I've got different film groups for instruction condition. But really, how many distinct populations do I have in this 2x2 design? 4, right? And so what I need in my set is some variable that goes through and identifies each one of these groups. I just included this in here because it makes it easier than you watching me go through and code stuff. But knowing that for your own stuff, when you go through to screen this, what you'll need is you need to create some variable in here that just identifies each one of these codes. And so I would encourage you to do the same thing so that you understand, so that it keeps track of who's what and sort of where people are at and things along those lines. Okay. So, but also important, anytime you open up one of these sets for problem set or anything else, to make sure that you have a good understanding of what's going on, what these variables represent, so that you don't sort of make mistakes and things along these lines. Okay. So what I'm going to do, I'm going to go through, and what you all should do is save this as a scrap set, right? So we don't fool around and irreversibly delete something that we need to keep in the set. Going to go through, I'm going to go and mark down. So I've got case 112, 32, and 200, mark down which condition these are in so I can go through and report this. If you look at the end of your screening document here, so we'll see, so we're going to report 3 cases with missing express scores. We've got someone in the sad withhold, sad express, and humor withhold, right? Always good to keep track, because remember with our screening, we're always looking for, like, are there patterns? Do I have sort of one condition where people are systematically failing out or something along those lines? So good to keep track of that. Here, we've got a lot of observations, right? We've got close to 200 observations. Am I too concerned about 3 scores with missing? No, as far as video went out or who knows what happened there. So going to mark it down, but not going to worry probably too much about this. Okay. All right. So What we're going to do, just like we did before, steps for the screening here are going to follow the exact same steps as we did for the one-way. It's just we have more groups to sort of deal with. And so then it starts to become a management issue on how we're going to go through and work this. So I'm going to go to data. I'm going to go to split file. And I'm going to look at this condition variable that I've created. Okay. Split file by this, and this is just going to break everybody into individual groups. We go through a split file, and then we're going to analyze descriptives, and then I'm just going to get my descriptives, right? Just have expression rating. That's my only outcome. Okay. But I'm going to save z-scores for this, right? And options, ask for skew and kurtosis here, continue, and then go through and paste. Okay. So hopefully you're starting to see how with the screening, sort of keeping good. Sometimes people are uncomfortable with the syntax stuff, but after you sort of do this over and over and over again, it starts to become nice because you kind of have a record of how you've gone through and done it. If you've done a good job of annotating sort of what's going on with things, and pretty soon you don't even have to necessarily worry about pull down menus. If you know the procedure, you just kind of copy over syntax files, put in the right variables. But if we go through and we do this, we run our outcome, or we run our output here, what we're going to do is we're going to get descriptive statistics for all four of our groups. Okay. All right, Emily, what are you seeing in terms of this initial descriptives table? And again, it's on your, if that's easier to see, all the values are the same. Yeah, yeah. So we're pretty good. So we can treat this as a sort of relatively balanced design. It's not identical, but it's pretty close, right? So the difference between 44 and 51, you got a 7-person difference, but with the size of these cells, it's sort of reasonably balanced. Okay, so we're happy about that. What else are you seeing? Even before we jump into skewness, what's the other thing we might want to take a look at? Yeah. Okay. Are our scores reasonable? Looks like they are here. Good. Skew and kurtosis. Okay. Someone help out. What do I mean? If we're using like general or something that might start to catch my attention, right? And is not the end all be all, but what are we thinking about in terms of for skew? What's that? About two, right? And so, and we've got reasonably sized cells here, which starts to give us semi-okay sort of visuals of our distribution. What's the thing with these data that might start to impact what our graphs are going to look like? A decent sample size. What about the nature? What are we measuring? What's our outcome? Emily? It's an observer rating, and how are they rating that? 1 to 5. Okay. Continuous not really. This is ordered categorical, essentially. Now we're going to treat it as continuous, and this is really there's only 5 options in terms of what these variables, and so that's going to start to impact what our graphs look like, right? So, but again, one of the things that start, if I have a 5-unit score, if I'm thinking about extreme, or a 5-unit scale, if I'm thinking about extreme scores, how extreme can a score be? It's kind of limited, right? So taking into account, what are we measuring? What's the level of measurement? Starting to understand some stuffs here. So we've got skew, looks okay, sort of slight positive skew on everything. For the humor inhibit, we've kind of got the most positive skew, but it's still not anything that would cause us to be concerned about anything. Kurtosis, we've got some negative kurtosis, which seems kind of boxy. We said positive kurtosis, which is sort of different, but again, nothing that should be causing too much of a concern here with our stuff, right? So anything that is throwing up red flags in terms of our distributions, not too much, okay? So what I'm gonna do now then is go through and just take a look at our distribution. So I'm gonna go back to my set. I'm gonna just sort the file just so it turns the split off. Now I'm gonna go to descriptives, explore. I'm gonna look at my expression ratings as my dependent variable. I'm gonna go down through and I'm gonna drop condition into my factor list, right? And that's gonna split everything up, look at things differently by condition. And I'm gonna take subject number and I'm dropping it in my label cases by. And again, that just means for my box and whisker plots that anything that's an extreme value will start to be labeled with the participant number as opposed to where it happens to be in the order of the set when I ran it. So we're going to go down to plots, request histograms, and then I'm going to hit paste here. Okay. Go through, run that. Bunch of really cool statistics, but nothing we need to sort of work on right now. And so just going to go down through and take a look at my histograms here. So Matt, what am I seeing here for my sadness express condition? What am I seeing? Yeah, it's just kind of positively skewed. It's a really actually a really impressive step distribution there, right? We can see that we've got ordered categorical data, right? But again, always wanting you as you're going through and doing this, not just do it to do it, right? Looking at this and saying, does this make sense given what I'm asking people to do, or sort of what am I measuring? Does this make sense given what we've asked people to do? Oh, yeah, yeah. Yeah, right. So what are we seeing in general here based on this plot? What's that? Well, so it's all, they're just sort of expressing, it is just a global expression. So they're watching, so but what's generally going on in terms of people's expressive behavior here based on this plot? Okay, so sort of given this distribution, thinking about sort of your x-axis sort of reflecting expressive behavior, what are we saying sort of, what would we infer about what's going on in terms of people's expressive behavior based on this histogram here? Do you have ideas? Uh-huh. Yeah, yeah. So just low levels of expression here, right? Like in general. So these are people who are, we just show them a sadness film and they just say, so just go ahead and watch it. We actually don't say anything about expression. We just like, oh, go ahead and watch this naturally and then record their expressive behavior, right? But what we're seeing is generally kind of low levels of expression sort of in response to this sadness film. Just like left to their own devices, people aren't really expressing a whole lot. And sort of as some people are, some people get sort of, we've made some people cry here, right? Because it's a super sad film, but like sort of in general, not a whole lot of expression going on, but about what you would expect. Most people sort of, it's a film stimuli, and so they're kind of doing their thing and then kind of going on. Okay. Yeah, Kitty. Well, if we think about sort of, if this is extreme intense expression and this is no expression at all. Yeah. Okay. Yeah. It's just a 1 to 5 scale where 5 really intense global expression, right? So we have a couple of people with some pretty sort of extreme reactions to this, but for the most part, we're just seeing people sort of not sort of give much, at least from an outside perspective, for someone who's watching a video could go through and rate, right? So again, with these types of designs, important things to think about, like sort of what's actually happening in terms of my stuff. I can calculate a mean score for this, but this contains a lot more information in terms of thinking about what's actually happening with folks. Okay, so we got that. Dropping down. Okay, what's happening here? So this is inhibit, sadness inhibit. Matt, what's happening? What are you seeing here? Yeah, which means that sort of what? Are we get people in the inhibit condition? Are we getting people that are expressing large amounts of behavior? No, right? So the max score we have, it looks like we probably got one person who got rated as a 3, and then after that, there's not much else going on, right? So we've got a really blocky distribution consistent with some of that negative kurtosis. So the vast majority of people are still sort of not expressing things, but the range of expressive behavior we get in this is less, right? Are we excited about that? Yeah. I mean, it's suggesting that when we tell people to shut it down, they're able to shut it down. So this is probably a good thing, right? If we go down and we take it, okay, what are we going on here? Amanda, what's happening here with this graph? Uh-huh. Yeah, right. So we've got the humor film looks like it's getting more of a reaction, an observable expression reaction out of people, right? And so that's an important thing to think about in terms of interpreting things. We're kind of around this sort of middle thing, still not huge, right? We're not getting a ton of reactions out of sort of the modal person, but we're getting something that's not nothing, right? And if we think about the type of thing that we're trying to manipulate here, that kind of makes, so if you think about like how we express sadness and how we express humor is kind of more of an observable thing. So this is good. It's kind of tracking onto sort of what I would hope. And then last, Teresa, what are we seeing here for humor inhibit? Yeah. What does this look like? How did you gauge this relative to the sadness inhibit condition, though? Stuff's leaking through, right? Some people really think this is a funny film, right? And even though they're trying to inhibit expression, most people in general, we're saying that this is probably pretty successful, but there's more leakage going on here in terms of express behavior for the humor film than there is for the sadness film, okay? But again, anything that's sort of going on that makes us super concerned about the overall distributions? Probably not. If we take a look at our box plot, Sam, what are we seeing in this box plot here? Uh-huh. Yeah. So if we're just looking at that sort of phenomenologically, what's happening? Well, I'm getting sort of median values, sort of value of 2 for sad express versus 1 for sad inhibit, right? And so we're just kind of seeing here, we get looking, so we had saw before, sort of more behavior, sort of response to the amusement film. In humor inhibit, again, it's sort of relative to this, we see in reductions, but median value is higher for humor inhibit than it is for sadness inhibit. And then we got some breakout folks, right? We've got some folks who either weren't listening to instructions or weren't able to inhibit. Are we concerned about these folks? Yeah, why not, Emily? Why are you shaking your head? Yeah, right. So what we're saying from this is that it looks like sort of instruction to inhibit, even though I'm assuming that these people listen to instructions and we're trying, that it's not always successful. And looks like it's maybe easier to shut things down in response to sort of mask sadness than mask some humor stuff here. Okay. So overall, are we concerned about anything we're seeing? Not really. Things are looking to be pretty good. So what we're going to do now, kind of record that. And then what we're going to go through, I'm going to take my split file and I'm going to go down through resplit, but this time I'm going to ask for Z express, so my Z scores, and then I'm going to take off skew and kurtosis because I don't care about that. Okay. And then just going to run that full thing. All right. Elizabeth, what am I looking at here? Yep. And why am I interested in scores? Compare for what? Okay. Yeah. What someone help her out. Why are we looking at Z scores? What are we trying to accomplish here with this point in the screening? Yeah, looking for extreme values, right? So what's nice? Oh, there's someone has a score of 68. Is that an extreme score? Like, who the hell knows? I don't know. I don't know the scale, right? Here, what we can go through is look at respective to each individual group. Do we see sort of inordinately high? I'm saying zeros, standard deviations of 1. That's always good. That means I've done what I was supposed to do, right? Look at the min here. So Sam, are you seeing anything in terms of min and max that is concerning with respect to extreme? Not. Yeah. Yeah. So we got a max on humor and inhibit. But if we go back to when we take a look at that plot, does that make sense? Yeah, we've got a couple people who at least one person who had some breakout stuff. So, but again, important to know, important to recognize, but probably nothing that is extreme enough for us to worry about it and do anything. This is someone who is exhibiting behavior that's important to take into account for, because not everybody is going to be good to know, but really not. If we go through and take a look and pull all this together, right? What we've got here, the big trick with, as these screenings start to get increasingly complex, is how do I go through and organize this in a way that sort of communicates things efficiently. Same template right here, right? But we're talking about sort of taking, accounting for missing cases, accuracy of plausibility, kind of what we've got in terms of after we get those out. And then what we've got here is just setting up, looking at the distributions for each one of our groups, right? Same thing as we've done before, but again, really trying to organize this. And again, this is more a pitch for CJ and I's sanity than anything else, but just kind of sort of going through and crafting these up so that we can sort of very quickly go through and efficiently sort of see your assessment of sort of this different stuff. Again, outliers, extreme values, what's going on here. Now, what we'll see when we go through and we actually run our ANOVA model, we'll see that we do have some evidence of a violation of homogeneity. And so we'll have to think about what we end up doing with that, right? So again, saying that it looks like that we may not have constant error variance across each one of these cells, but that kind of makes sense too, given what we've seen in our screening, is that it looks like, if I'm looking at SAD inhibit, people were pretty good at that. So we range of observed values only went from 1 to 3, right? Versus humor express a lot of variability across that, right? So this probably shouldn't make us too surprised that we're seeing this. So in terms of recommendations, 3 values with missing, possible violation of homogeneity of variance, say we're relatively balanced, minimal missingness. Distributions were generally not normal or symmetrical, but probably not problematic given assumptions of normality of the sampling distribution and the size of our respective cells, right? We see some evidence for violations of homogeneity of variance, suggests that we continue on with our 2x2 factorial design with potential adjustments for omnibus and follow-up tests given violations of homogeneity of variance, okay? Yeah, I don't know, sort of normally, sort of previously, it was hard to get SPSS to do this unless you sort of converted over to a completely different analyses. Now we have some options where SPSS will provide robust estimates within the ANOVA sort of module, which is helpful. Read a paper that sort of has been out for a while, but in talking about sort of looking at the assumption of sort of these that we've talked about, so that the robustness of some of these tests and some questions about the extent to which that is true or not. So we'll go through and look at the omnibus test for this in a couple of different ways with sort of our standard estimation and then also with robust estimation and sort of see if we catch any differences, okay? But overall, big picture is that screening for our factorial designs, following the same stuff as we did previously for our one-way ANOVAs, right? It just sort of we're dealing with more groups because we've got factorial, so we've got cross things, so we've got more groups to deal with, okay? All right, questions? Feeling all right with this? Okay, nice work. Thank you again, everybody, for all the work you put in. We'll probably finish up the week after Thanksgiving, or we'll be very close by that point. I'll go through, post up the problem set. So if you want to start picking on it over break, you can go through and do that. Only thing I would say is remember that what I want you to do is, again, so this will be sort of group-based project, so sort of break you into 3. So CJ and I, fewer sets to go through and do. So think about sort of organizing that and what that'll look like. And then you can kind of decide how you want to sort of go through and do stuff. So, all right, awesome. Nice work. Good luck with the rest of the problem set. Again, I'll be available via email-ish, but also CJ will be here. Then just make sure that you get that and all components in by Friday at noon. All right, awesome. Nice work, you all. Enjoy your break, and we'll see you after Thanksgiving.